Good morning. Let us start. So we now continue the same exercise that we started yesterday. And I asked you to try to fill in these cells. Sorry. I asked you to calculate this value and then to fill these cells. And to fill also this one. So let's see. Please type I11. What values did you get here? Who tried to calculate? What values on the cell I11 did you get? .042. Okay. Yeah. All right. You seem to be in very nice agreement with each other. Yeah. I see some people are still typing. All right. Interesting. Very interesting. Yeah. Let us now try to calculate together. Yeah. Square root. And now we have to add all the squared standard uncertainties. Yeah. So let's start looking at this one. Is not standard uncertainty, has to be divided by square root of 3 in order to make it into standard uncertainty. It is easier to do it in such a way that I take this to the square and then divide by 3. So I don't need to take square root of 3 and then afterwards take it to the square. No? Okay. This one already is standard uncertainty. Yes, you may say that, wait a minute, it's a 0. Why do we account for it? But you see, in some other case, it might not be 0. So we still take it into account. Yeah. Then there's the temperature. Here we already divided by square root of 3. So this already is standard uncertainty. We simply take it to the square. Yeah. And finally, this one again is plus minus, so we sort of again assume rectangular distribution. So we take it to the square, divide by 3. Oh. And it seems that I am at odds with what you found. Was there any student who found 0.025? Did anybody get? Brackets? Gleb, I will come to the brackets. Yeah? One moment. I simply would like to see, did anybody get this this 0.025, or really all of you got 0.043? Hans already answered Gleb's remark. Yeah. Okay, apparently nobody got 0.020. Yeah. Now, let me also explain or come to Gleb. In Excel, there is a hierarchy of operations. The lowest operation is plus and minus. The next is multiplication division, and power is the highest. So always first the power operation is done, and only then any division, multiplication, etc. is done. So yes, we can. It's absolutely not forbidden. And if you are unsure in yourself, you can put these brackets, yeah, but you see you get exactly the same number. Yeah. Gleb, I hope I managed to explain. All right. Now, okay, we managed. So now this is a very good, like a very instructive case that you always have to think that you have to calculate standard uncertainty, and for calculating standard uncertainty, you have to convert all the uncertainties into standard uncertainty. All right, now let's go here. What did you get here? What value did you manage to get here in cell B17? This should be easy. $11.80. Okay, let's see. Here we simply calculate the average of these values. Boom. Yeah. Exactly as you say, 11.827. Yeah. Good. What did you get here now? Repeatability. Yeah, this is interesting. Let's see what you now got. Yeah, please type what you got here. Cell E17. 0.13 something, yeah, let's see, one. Also 0.13, let's say 0.14 if we round. Anybody else, anything? 0.23, so this time we have debate, yeah. All right, so this is obviously standard deviation of these. But if I would just stop here, this would give me the standard deviation of the individual value. But for the calculation of our result, do we use any of these individual values or do we use the mean? We use the mean. No? So probably it's a good idea to have here standard deviation of the mean, which means that we also should divide by square root of number of measurements. Yeah? And perhaps I will even do it in such a bizarre way that I will not put here square root of 3, because this might leave the impression that for some reason I'm converting rectangular distribution uncertainties to standard uncertainties. I will instead write like this. This is not really very important since this is so small number of values, but this gives the clear idea if you later read it that okay, it's the number of measurements that matters here. So indeed 0.137 is the correct thing. Please now here I can actually do very conveniently with this polling feature. Yeah. Who understood why we need to use here standard deviation of the mean? Who understood why we need to use here standard deviation of the mean? Yeah. Okay, you can raise hand, but you can also do this poll. I started a poll. If you understood, you put true. If not, you put false. This has the good possibility that nobody except me, nobody sees what you type. Yeah? So one person doesn't understand, all the others understand up to now. Okay, some people have not replied. Okay, I stop here. Some people did not reply, but obviously most of you understood. One people did not understand. Yeah. Let me try to now to explain again. Usually we use standard deviation of the mean if in our further calculations we also use the mean value. And here, this is exactly what we are going to do. Yeah, we did not yet calculate the result, but for the result, we obviously will use this number as the value of the titrant volume, yeah? Not just randomly any of these four. In principle, we could just use randomly any of these three. This does not really make sense, yeah? We use the average. And the repeatability of the average value is conveyed by the standard deviation of the average, which we of course get by dividing by square root of number of measurements. Was it understand? That person who did not understand? Ah, okay, good. Yeah. Fine. Now let's move to the temperature. Did anybody try at home? What value did you get? Hmm? 0.072. Here I take a liberty of being lazy, and look what I'm doing. I'm simply copying this equation here, because it happens to be just at the same distance as it is here. Yeah? So that yes, 0.0072 is correct. And now finally, systematic or possible systematic effect of endpoint or equivalence point. Yeah. This is now something that can obtained by, for example, doing in parallel potentiometric titration, but also putting indicator into the solution during potentiometric titration, finding out when indicator changes the color, and then finding out when from potentiometric titration, from this differential curve that I showed last time, when the real equivalence point is, and finding how big is the difference. And it is, of course, possible that depending on the amount of acid and the amount of concentration and then some other things, this is not always the same, yeah? So it can be simply just random effect. We see already random effect also pretty significant here, yeah? But there still can also remain some systematic effect. And this is now a nasty part or an inconvenient part for the ISO GAM in the sense that this oftentimes has to be done just by expert opinion or educated guess or experience from the past. A fairly good estimate here is 0.2 milliliters, plus minus again. Oh. And now, what you can do, please now try to calculate cell I-17. So please, all of you take time, calculate the cell I-17 and type here what you found. No? Also GAM. Yeah. Can I show formula? Gleb, you can download the file from Moodle where the formula is in, but of course I'm not, it's not difficult for me to show the formula, so please, here it is. Yeah. Louis says, Ivo, I'm not sure if in the calculus under the certain V sample the square are present in the equation. Louis, what cell are you referring to? I11 happens to be just pictured for you at the moment, and you see these threes are square roots of 3 taken to the square. And the square from square root of 3 happens to be 3. Did I manage to persuade you? All right, yeah. You see, it is also possible here to write divided by square root of 3, then put brackets and then put this square, but it's so like clumsy and unnecessary. Yeah, this is much more elegant way of writing. All right, Sarah got 0.18. Let's see what others get. Yeah. Also 0.18. Ola got 0.14, 0.18. Okay. I am again lazy. You see, here we have plus minus, and here we also have plus minus. Here we have standard uncertainties. Here we also have standard uncertainties. Here we have plus minus. Here we also have plus minus, meaning I can simply copy this equation here. That's it. This cannot be always done, yeah? Because if here would be, for example, this would be standard uncertainty and this, then I can still copy, but I need to modify. But now I could just copy easily, and this is how it looks like. Okay, here we seem to have a nice consensus. Oh, by the way, number of decimal digits. Again, as I said, in interim results, we don't need to be strict. But here, of course, it's beyond any reason. There are far too many. The only reason I keep it so big, this number, is that you can all check your calculations. If all is right, you should have exactly the same digits in your cells also. Sometimes in uncertainty calculations, mistakes are very subtle, so that the first digits will be the same, but the latter ones will not. Yeah. This is why I'm keeping quite a number of digits. Okay. Now, something that we perhaps should already have done is calculating our result. Yeah, so the result value. Please now, everybody, try to calculate this result. You have the formula here, yeah, very easy. And now try to do the calculation and type what you got. Calculate the value and type what you get. All right, let me try also. Equal to titrant volume multiplied by concentration divided by 2. Multiplied by molar mass multiplied by 100 divided by sample volume. Oh. Okay, yeah. Here apparently we don't have any discussion. Now the next thing to do is to figure out how we can calculate uncertainty. And for that, we take the slides and let me find. Okay. Does any of these work for us? If we think of our model, which of these approaches we can use at the moment? Yeah, Gleb says slide 7, Komal says multiplication 1, which is the same, yeah. And Ola says, but you can also use universal derivative. Yes, we can, Ola, indeed. We can calculate partial derivatives from everything. It's absolutely allowed. We could, in principle, do analytical partial derivatives. This is not very difficult equation, but these analytical partial derivatives would still be quite clumsy. Yeah? It's quite a bit of work, actually. Yeah? Later on, we will learn a spreadsheet approach for calculating partial derivatives, which is easy in the sense that however sophisticated is your model, calculation partial derivatives is still very easy. But today, in the interest of time, we will use this multiplication thing. For that, as you see, we will need relative uncertainties of these quantities. Yeah? And we calculate this term from relative uncertainties. And then we multiply by the value of our output quantity, and we get combined standard uncertainty of the output quantity. So let us now try again to do this in our case. We first need the relative standard uncertainties. Please note that all these uncertainties here are absolute in the sense that they are expressed in the same units, so that we need to modify or we need to calculate. This is, of course, very easy. Uncertainty divided by value. Uncertainty divided by value. Uncertainty divided by value. And please now try to calculate the combined standard uncertainty of the acid concentration. I will wait a bit and then I will also calculate, but whoever gets it calculated in the cell I28, please shout. Or, I mean, please type the number into chat. Okay. We have 2 times 13.4. Let us see. I will also try to calculate. Equal to. We need to multiply by this value and then square root of sum of squares. Now, very useful operation. I think I've already, no, sum sku I haven't yet introduced. It was sum product. So sum sku is very useful if you want to simply sum the squares of some array. Yeah. And 13.39 it is, exactly as you calculate. Now, in principle, we have managed to calculate the uncertainty, yeah? Or in principle, we could stop here, yeah? Value is here, yeah? Combined standard uncertainty is here, so we've essentially managed our task. But let us go a bit further. First of all, we would be interested to see where the uncertainty comes from. As I already explained, it's a very useful property of this ISO-GAM approach that we see where which input quantities most contribute to the uncertainty. And secondly, we would also like to calculate the expanded uncertainty. And we would like to know whether it is like normally distributed, is K2 uncertainty corresponding to 95% coverage probability, and so on. For that reason, we now calculate the uncertainty indices. Yeah. And if you remember, uncertainty index was, or perhaps I will show you for a moment. Uncertainty indexes are calculated like this. I think I have it somewhere here. No, I had it here. What? Index of a specific component is the square of that component divided by the sum of squares of all components. Now you may ask, what is component in our case? And in this case, we use this formula. In this case, each of these relative uncertainties are our components. So, for example, this is one component, yeah. This is one component, etc., etc. Yeah, this is one component. So, try to calculate now the indexes. And who gets the index of CT? Let's take the first one. CT calculated, type it here. You see, Gleb, this is again the same issue as what I said already, like in the very beginning. Whenever we sum or subtract uncertainties, errors, standard deviations, etc., we do all manipulations with squares. And afterwards, if needed, we take square root. Mathematical statistics people actually oftentimes prefer not to speak about standard uncertainties at all. They speak about dispersions. And dispersion is the squared standard uncertainty. Gleb, did this help you? Okay, I got also 17.17. You see, Gleb, indices do show contribution. We need to have them squared simply because for calculations we also take squares of uncertainties that we combine, not individual uncertainties. This actually has a very important consequence. This squared summing rule means that bigger components eat up small components. So what usually happens is that if one component is 5 times smaller than the other one, then its contribution essentially becomes negligible. Only 5 times smaller. If we would simply add, would not be negligible at all. And indexes have to convey the same logic. Let me give you this demonstration here. Suppose we have 2 uncertainty components. One is 5 and the other one is 1 unit. If we would simply sum them up, we obviously would get 6. Yeah? But if we sum them up with the squared logic as we do, yeah, SQRT, sums Q, yeah, we get 5.1. So see, this bigger one essentially destroys the influence of the smaller one. Here it counts as 1 unit. Here it counts essentially as 0.1 unit. This is very consequential. This is why in lecture in several times I have stressed that all important uncertainty components, usually being smaller by 5 times from the biggest uncertainty component, is sort of borderline when an uncertainty component becomes unimportant. So suppose if this were now 0.3, or let's put 0.5. See, if we just neglect it, our uncertainty will be 5. If we put it in, it will be 5.02, which in any conceivable practical application is insignificant difference. Claire,
I'm really sorry to stretch it for so long. Just to clarify one last moment. So when we calculate uncertainties, we take squares, and then calculating indices, we take squares as well. So index like conveys more the 4th power of the original value, not the square. Or am I somewhere wrong with this logic? I'm really sorry to stretch it for so long.
No, Gleb, you absolutely don't need to be sorry. I will be happy to explain, and please never hesitate to ask. No, it's not 4th power. I don't see where you get the 4th power. Indexes themselves are simply standard, the relative uncertainty or components in our case are simply, the components are simply relative uncertainties. And now we operate with squares of relative uncertainties. I don't get it where the 4th power comes in.
So it's more like the relative uncertainties were calculated from absolute uncertainties, which were the 2nd power.
Now I see. You are probably implying that here we already used 2nd powers, meaning squares, right? And now we are taking another square. Is that what you mean?
So it's cancelled out because of the square root, isn't it? Now
Exactly.
I get. Okay.
You are reading my mind, yeah. Yes, you see, we calculate them via squares, but in order to arrive at something that carries the same unit as this one, yeah, and that can be really added and subtracted, we obviously have to take square root. You see, always the result and the absolute uncertainty obviously have to have the same unit, so it cannot be that one is the square of the other. Yeah? This is also why analytical chemists don't really use dispersions that statisticians tend to use, because analytical chemists always work with something that has units, but for statisticians, that's not the most important thing usually. They simply look at numbers. All right, let me make a poll about this. This is actually pretty important. It's good that I explained it here. Who thinks that understood how the squared summing rule destroys small components and fortifies big components, suppresses small components? Who thinks that understood from my explanation? Okay, not everybody has answered, but everybody has said that understands. Okay, then I think I can stop here. All right, and Gleb, no shame on you. We are here learning. Yeah. So all questions are welcome, and yes, if there are misinterpretations, then it's my job to clarify. Yeah? All right, so now we got this first index calculated. Now, you notice I have put here dollar signs. Let me now do another poll. Who understands why I'm putting dollar signs into this formula? Who understands why I'm putting dollar signs into this formula? Okay, again, everybody but 2 students have answered, so probably it's okay and understandable, yeah. So the obvious answer is, of course, that I want to copy this formula, and the typical addressing of Excel is always relative. So this address will always be changing to E28 and then to F28. But if I want to fix this D letter, I have to put $sign in front of D letter. Yeah? All right, here it is. Good. I guess you probably got the same indexes, yeah? And I now save the file in case anybody needs. So, obviously, most of the uncertainty comes from measuring the volume of the title. So, here we already can make some conclusions. Is there any point of buying a better pipette here, or maybe calibrating this pipette, etc.? What do you think? Should we put a lot of effort into improving the pipetting? Yeah? Luis says no, and yes, I fully agree. It only produces 2% of uncertainty. This does not mean you should pipette in a sloppy way, but buying something much more expensive probably would not make much difference. Okay. Instead, we should put all the effort into these. But now this 80.62, it is actually composed of a number of different things. Yeah, there are 4 different things. It would be useful to see how those different things make up this 80.62. So please now try to calculate the indices of all these components here. Yeah. Please now try to calculate those indices. And please note that there's a separate line for standard uncertainties, because not everything is standard uncertainty, but for calculating indices, you need that all of these are presented as standard uncertainty. So please try. I will also try. Let me now wait a little bit. So whoever gets repeatability index, so the index of this repeatability component calculated, please let me know. Whoever gets this calculated, please let me know. Gleb says 58. All are also 58. Kavintat also essentially 58. Okay, it appears that you have mastered this art pretty well, yeah? And again, we put dollar signs and we copy. All right. Here it is. And 58 it is, or 57.97. So we see that our biggest component is titrant volume, and in turn, most of titrant volume contribution comes from repeatability. So in this case, repeatability is indeed something we should take care about. So if we want to improve our method, then obviously there's no point in buying much better titrator or thermostating the room. Yeah, let's observe that temperature uncertainty here contributes 0.16 only %. And we were very generous actually with temperature. Yeah, we put here plus minus 5 degrees, which is a lot, but obviously temperature is not really an issue at all. So buying a better air conditioning system for this analysis is certainly not necessary. Yeah. So we should put all the efforts into this, and also this systematic effect of equivalence point is certainly a problem. And now, as opposed to this visual indicator titration, what would be your proposal? What should we do instead? What kind of titration? What would be the most obvious and straightforward way to improve the measurement uncertainty here? Get lower uncertainty. More replicates? Possibly, yes. You are right that it will decrease this one, yeah, but it will not influence this one. Moreover, it makes the analysis longer, yeah, people need to work more. And Lewis says potentiometric titration, and I would probably also go for that, because potentiometric titrator would attack this systematic effect and this random effect, both of those, just by using the differential curve, which I explained somewhere. So potentiometric titrator would give us this thing. Yeah? And now, obviously, this top here also has some uncertainty. It does not mean it does not have any effect. But since it corresponds to the fastest increase of pH value, then it's very close to actual real equivalence point. There always remains some repeatability issue, but otherwise, all this thing that we don't see visually when indicator change color or don't understand, or that indicator possibly changes color at the wrong moment when equivalence point is not achieved, all these problems get very small, even with this miserable the titration curve that we have. All right. Now, what do you think if we now go to this small thing? Oh, this one. If we take now this simple European accreditation guideline, can we consider that our measurement result is normally distributed? Can we consider that our measurement result is normally distributed from these data that you right now see in front of you? You say, Luis, that we have small number of repetitions, which is correct. But is this quantity, which has a small number of repetitions, is this one of the dominating quantities? What do you think? Yeah. Kwok says we have three quantities, but they don't have comparable magnitude. Yeah, true. Okay. If we now think what is said here, then in this point number 2, obviously we don't have such a quantity that is a main source of uncertainty and has 30 or more degrees of freedom. No way. And also, we don't have 3 dominating input quantities. In fact, we have a purely dominating titrant volume, and in titrant volume there are 2 dominating components in turn, which is repeatability and systematic effect of the equivalence point. Moreover, the single biggest uncertainty component is repeatability in this case. And that is obtained as a mean value of only 3 replicates. So that, let's see, yeah, we are exactly here. We have an important input quantity which has small number of degrees of freedom. So that we should go for this Welch-Sutter-Dwight approach. Yeah. So let us try to do that. But that will now be not as easy as you may think. Yeah, but we will, of course, try to manage. Okay, it would be very easy if now we could just work with these quantities and assign number of degrees of freedom to each of those. Out of curiosity, what is the number of degrees of freedom of titrant concentration? What do you think? What is the number of degrees of freedom of titrant concentration? Zero is not correct. Louis, sort of, yeah, but could you be more specific? Yeah. Could you quote any number? Exactly. We could say 30, 50, or essentially any big number. Because, let's face it, this is a B-type quantity, typical B-type quantity. This is 0. We don't need to think about it. This is B-type, and this is also B-type quantity. So essentially every uncertainty source here is B-type. Yeah. And B-type quantities have an infinite number of degrees of freedom, or we can take 30 or 50. Okay, good. Oh, sorry. I was speaking about CT and now I jumped to V sample. In CT also, we have only one uncertainty source, which also is B-type. And as I already explained, V sample also we can consider a B-type quantity. So both of these would have effective number of these degrees of freedom, for example, 30. But here, it's neither A nor B by itself because it has several B-type components, these two and this one. So 3 of the 4 are B-type, but this one is A-type quantity. So that just to this UREL-VT, we cannot really assign degrees of freedom in a reasonable way. So what we will do, we will break it into 2 pieces. We will break it into 2 pieces. And let's see how we do that now. So, okay, first of all, let's try to work with these 2, which is easy, huh? So the index here is the same. Number of degrees of freedom, 30. Good. Here, the index is the same. Number of degrees of freedom, 30. How do we now get the index of VT, which is specifically about repeatability? Let's see if anybody can figure that out. Let's see if anybody can figure that out. Yes, Carlo. Yes, Luis. Very nice. Yeah. So multiply this one by this one. Now it gives very many of these. Yeah, let's see. No. Okay. And here now is a good demonstration why I don't favor presenting percentages by multiplying with 100. Why instead I prefer to format the cells accordingly. Because otherwise, now, as you multiply 2 percentages, you must always keep in mind that you still need to divide by 100. But right now, I never really think about this 100 at all. I simply multiply the way I like, and that's it. Yeah. What is the number of degrees of freedom? of vrep, or this URL VTREP. What is the number of degrees of freedom? N minus 1 is 2. Yes, very small number. What is now a very convenient way of calculating this VT other? How would we find this VT other? URL VT others index. Same as F32, but multiplied by 1 minus E19. Yes, it is. This is maybe even the simplest way, yes. Another possibility would be take 1 minus the sum of these three, because the sum of all indexes always has to be 100, but they will lead to exactly the same number. Yeah? So let's do it the glad way. Yeah? In any case, there's no need to start adding all these F19, G19, and D19 together. And always what we can do, we can mark all these. And when we see here, you see Excel here, down here, calculates the sum. Yeah. So this sum always has to be 100. All the indices have to sum up to 100. And what is now the number of degrees of freedom of this VT other? What do you think? Number of degrees of freedom of this VT other. Why 30? Who can explain? Also big number. Yeah, why big number? As they are B-type. Yes, okay, yeah. Probably I will not manage to fool you. Yeah, all these three things are all B-type. So yes, we can be confident that it's just a big number, which we can take 30. And now let me take the slide. Where is the Welch-Satterthwaite formula? Oh, and now, as I explained, the typical Welch-Satterthwaite formula that you see in most materials is this first one. So this is the like mostly pictured. But in fact, in most cases, I have found this is more easy to use and like more convenient. Yeah? So that instead of using these fourth powers, you can use indices to the second power. And you may remember indices already themselves contain second power, so that this fourth power that is meant here actually is also realized here. Yeah? Simply, you don't need to carry out all those things. Also, these U's are not the U's of the input quantities. They are U's of input quantities multiplied by this sensitivity factor. In our case here, they can be interpreted as the relative standard uncertainties, but sometimes it can be more complex. Yeah? So in any case, with these indices, it is very simple to calculate. And I have termed these things as Welch-Satterthwaite components. So please now try to calculate into cell D35 the overall number of degrees of freedom. whoever gets it calculated, type it here. I will also do the calculation, but I'm not showing you right now what I'm doing. Yeah, so that you can do it yourself. So Gleb gets 8.77, Ola gets 8, Christian 8.77. You all are correct. If we simply calculate, we get 8.77. But numbers of degrees of freedom, exactly, Ola, they are always rounded down. And the function that we will be using for calculating now the corresponding student coefficient also rounds the number of degrees of freedom down. All right. So I share the screen again. Now I have forgotten to remove the formula from this cell. Yeah, very sad. Yeah, but yeah, so it is. But now you can see what is put here. So it's TINV. TINV is the two-sided student coefficient formula. 0.05 is probability, but it is like the probability in inverse. So if you want 95% probability, which is 0.95, you should write here 1 minus 0.95, which is 0.05. And D35 is the overall number of degrees of freedom. And I have also rounded the student coefficient to do decimals, but this is not really very, very important. Yeah. And we see that instead of student coefficient 2, in this case, we should use 2.3 if we want to get 95% coverage probability. So it is bigger than would be just 2. And now we can try to present the result. You can all now try to present the result. The result obviously is this one. This is now the combined standard uncertainty multiplied by 2. It is the K2 uncertainty. Yeah. And this is now the uncertainty at coverage probability for 95, which is 31. Any questions here? Did you understand this calculation? Probably not difficult to understand. Now, let us briefly look at how you present measurement results, meaning how many decimals, how many digits after the comma, or how many decimals. What I'm presenting here is one possible convention. Some other people may have other opinions. And I'm not saying that I am right, everybody else is wrong. Yeah, so I accept also other opinions. And obviously, this is not any kind of, let's say, question about scientific truth, because the numbers are what they are. Yeah? It's simply the way of presenting. But a fairly reasonably conventional is this. You look at the first significant digit of uncertainty. So whenever you present your result, you start with uncertainty. And if the first significant digit is 1, 2, 3, 4, you present with 2 significant digits. If it's 5 to 9, you present with 1 significant digit. There are quite a number of people who say that you should always present uncertainty with 2 significant digits. There are also people who say that you should always present with just 1 significant digit. Yeah. But it seems reasonable to do it like this. Yeah. Now, please raise or I'm now starting a poll. Who understands what significant digit is? How you determine which digits are significant digits in any number that is presented? Sometimes I have also had to explain this to people. Who understands what significant digit is? One person does not understand. Okay. And one person does not understand. Does not write anything. Okay. To be on the safe side, let me explain then briefly. Whenever you want to determine which digits are significant digits, you start looking at the number from the left. Let's assume we have this kind of number here. Yeah? Now, you start looking from the left, and zeros are not significant digits. Yeah? Small. Yeah. And now 0, 0, 0, you omit 3, 2, 3, and 7. These are significant digits. If it is presented like this, then the final 0 is also significant. So now it has 4 significant digits. Okay. And once... I hope this was understood. And once you have managed to find how many significant digits your uncertainty has, perhaps I even put like here. Yeah. Then for determining for the result, you look at number of decimals after the comma or after the decimal point, and this has to be the same. Yeah, okay, yeah. The number of decimals after the comma has to be the same in the result as it is in the uncertainty. So that if this is here 0.036, then 0.036 means there are 3 digits after the comma. So here we also put 3 digits after the comma. 0.09, 2 digits after the comma. Here also 2 digits after the comma. Now, in our case, the first digit was in both cases in the range of 1 to 4. So we put 2 digits. And in this case, it will be 0 digits after the comma. So here, no digits after the comma, and here also no digits after the comma. Was this explanation understandable? Yeah, let me again make a poll. Yeah, this is very clear. Was this explanation understandable? One person did not reply, but everybody else replied. So, okay. We consider it's probably okay. Now finally all replied. Okay, good. Was understandable. Then it seems to me that we have finished this example. Anything anybody would like to ask here? Any questions still? If not, now, good news. You are now well prepared to do the first homework. So you can now go to the homework section and start doing the first homework. This, what we did today, yeah, gives you all you need, yeah, for the homework. Sorry, for the first homework. So, if at the moment no questions about this, then let me stop sharing the screen and go to the slides where we left off. So this was the last slide that we actually looked at, yeah? We will do in Excel, we did in Excel, and now these all things we actually did already, but let's just click the slides through. So all the uncertainty components we converted, yeah, okay. Our model is this, yeah, so we do like this. This is exactly what we did. Yeah, we got the result. Yes, we've presented the result as at K2 level. Yeah, we'll do it. Can we assume normal distribution? No, we cannot. We calculated the indices. Yeah. And we also did some analysis of uncertainty contributions. And we found out that almost all of the uncertainty comes from dispensing the titrant, and that in turn is mostly composed of 2 big uncertainty sources: repeatability and possible systematic effect of determining the endpoint. And we also reached the conclusion that there's probably no need for better pipette, for better room conditioning, so the temperature uncertainty would be lower. We should put all effort into determining the equivalence point better, both from the point of view of repeatability and also systematic effect. And both of these aims would be served by a potentiometric titrator. Yeah, so this is where we should go. And now I have here another illustration for you for a much more sophisticated analysis. This is the same dissolved oxygen determination that I already pictured here. So from this analysis, where, as you see, the model has three components. So potassium iodate, yeah, this concentration of potassium iodate then is fed into this equation for getting concentration of thiosulfate, and thiosulfate concentration is then fed into this equation. So it's actually a huge model equation, yeah? And all these numerous input quantities have their contributions. And what I want to show here is that the same approach can be used. It's the same uncertainty index approach that can be used for getting all the uncertainty contributions, the uncertainty indices. And here they get the indices for the first. This altogether gets 13 point something, yeah, %. And then this feeds into the sodium thiosulfate, where there's volatilization of iodine, yeah, which feeds here. And finally, this is the uncertainty, yeah, and we see that the three main things are purity of standard substance and volatilization of iodine in this case. But please note, there's a very important thing here to note, that this is dissolved oxygen in pure water. If we now go to real sample, which happens to be seawater, then the dominating uncertainty components are completely different. It's mainly the interferences, and this is essentially repeatability. These gammas denote repeatability. Purity, which before was very important, is now 2.71%. Yeah. Volatilization, okay, it still plays some role, 8% here, 2% here, or 3%, so jointly something around 10%, but it's nowhere near these things here. Why I'm showing you this? This means that even if you get your uncertainty budget done, you should not very lightly disregard uncertainty sources that under some conditions seem to be insignificant, because under some other conditions they might be highly significant. Let us also go back for a moment. This standard uncertainty here, if you look at it, is something like 0.2% relative. So this is something like 0.2% relative if you try to calculate. This standard uncertainty here is much bigger. Yeah, it is difficult to calculate by it's to be something like maybe 0.4% relative, or yeah, maybe 2 times higher or so. And then it's no wonder, because new uncertainty components come in and significantly increase the uncertainty. in any case, this uncertainty still is very low. So most titrations do not achieve this low uncertainty. Any questions here? Okay, if no questions, it's 11:43. Yeah, this slide we don't need to discuss. We did already, and now there's the advantages and drawbacks. But this takes more time than just 2 minutes. So we will leave this for the next time. This is where we continue next Tuesday. Meanwhile, you are welcome to work with homework number 1. Yeah, it's not so difficult. Try it. Yeah, and next Tuesday, hopefully, we will be again back in the lecture room. But this afternoon, those of you who come to master seminar, this master seminar also is online. Yeah, so master seminar today also online, because I am not in Tartu. But for now, thank you and goodbye.